Perfect. It is a perfect time to talk about TidyModels and to do a demo on TidyModels. So TidyModel is we can write it here actually. Okay, introduction. Let's put it as introduction. This document supposed to say is supposed to show how TidyModels works or work at a minimum level. By the minimum level, I mean the level that is practical. You can follow to train and test models professionally, yet the process does not cover every single feature of the TidyModels. And the reason of being so is simple. First, I do not know every feature of TidyModels. And second, it is defeating the purpose to aim for a minimum working practical report or manual and then fill it with free-for-all features. Perfect. So it now must be clear. TidyModels has a rationale behind it, or at least one of the motivations behind TidyModels is simplicity. TidyModels have had several motivations behind them, but I'm not sure whether I should use it as a singular verb or a plural verb, but let's continue with the plural verb. So several motivations behind them, and one of them is simplicity of the process of machine learning and predictive modeling. Okay, so predictive modeling is, I'm using it as a supervised machine learning equivalent. You can argue that this is not the case, and yeah, we can continue with the discussion about it, but for now it's fine. The problem was having several main packages for supervised machine learning in R, such as MLR and Caret. And these packages had or have, or the problem is, well, let's say had, still they have. So the problem is having several main packages for supervised machine learning in R, and these packages have different interfaces, i.e. the arguments of the functions, and different data structure outputs, what their functions return. TidyModels tend to address these issues using a unified and simple interface output as close as possible to the, or better to say, under the Tidy dialect. Okay, so these are my understanding of the situation. There was we have a set of packages on machine learning, supervised machine learning in R, MLR, Caret, and more specific packages like GlimNet, and for instance Keras for machine learning using deep learning. And these packages, we have to learn every time how to deal with their functions. The interface, the arguments are different, the output is different, and then figuring out what to do for the cross validation and performance measurement, etc., etc. And we had the tidy dialect very well welcomed by the community. So the TidyModels, as far as I understand, was developed and is being developed to address these issues and to be the part of this ecosystem. As far as I understand, the TidyModels are being developed to address these issues and to augment the tidy dialect. So this document tends, okay, let's talk about the rationale behind this document. There is a rationale behind this document. When I first read about the TidyModels, I got very excited. I expected lots of unification and simplicity, and what I found was a large set of functions to learn. It was disappointing at first. Then, after further pondering and searching, I figured out that not all those functions are needed, and there is a simple logic connecting all steps and functions. This document is here to cover that simple logic and show the minimum number of functions necessary to do a machine learning project. Okay, so by now, in the first 8-9 minutes of this video, you have now very familiar, any probable audience would be very familiar with what tidy modeling is, the rationale behind it, and the rationale behind this document, why I'm writing this document. So it's a machine learning project, so let's start with the data. Or better to say, let's start with the libraries. And the libraries, I'll start with tidyverse, and then we have TidyModels, and later on we'll come back to talk about the do parallel for parallelization and some other libraries. So let's run these. And now, what about the data? Data can be anything here. You can find a very messy real data. You can work with a simple data set. I rather start with a synthetic data set. Because I can determine the ground truth of this data set, i.e. the irreducible error. Okay, I can set that how much at best a model can perform on this data set. So how to do so? Let's define a table with x a random number starting, so 10,000, mean is equal to 1, and standard deviation equal to 2. Okay, so if you run it, you will get this x, and we can change it to x1. And so this is the end, or better to say, this is the end of the first function, the tibble. And then I define x2. And x2, let's say that it is another normal distribution, and 10,000 this time mean equal to let's say 0.5, and st equal to 1. Okay, and then let's define a y, and the y is designed by combination of a function of x1 and x2. And what combination? So x1 plus x2 power 2 plus r norm n equal to 10,000, mean equal to 1, and st equal to 1. And so this part will define the irreducible error, because even though the model can capture this relation, they cannot capture this random set. Okay, and we can change it a little bit to make it a little bit more difficult, plus sine x2, and yeah, so I'm not sure whether how the sine would react, so let me try it. So what would be the sine of, so it's 1.5 equal to 1, sine 1 equal to and what about sine 0? It is 0. Good. So I think that this is good enough. We have x1, we have x2, and we have y. So let's assign it to data table. This is our data set. So far, so good. And we can get a glimpse out of it. Okay, 3 variables, 10,000 rows. Okay, so here we call it tidy modeling. And the first step in tidy modeling is data split or partitioning. In different sources, these two terms are used interchangeably most of the time. So let's do it. To do so, the TidyModels package, which is actually a meta package, an umbrella package covering a set of packages. To do so, the TidyModels package has a package called R sample. So if we use this R sample or resample, R sample, yes. So we have this initial split, and for the initial split, the data is equal to data table. The proportion, let's say that we have 0.8 for the training and 0.2 for the test. And there is a very nice argument, strata. It is for a stratification of the sampling. Okay, and especially it is important for skewed or imbalance target variables. Depend whether we are talking about regression or we are talking about a classification problem. So for the strata, I will set it to y, the outcome or the target variable, because we want our samples to have similar y or the target variable distribution. Okay, their distributions we want to be similar. We don't want the training to have all the simple observations, and all the difficult observations would be located in the test, or other way around. Okay, we want both training and testing to be very similar from the point of view of the target variable. So let's call it data initial split. Okay, and then we need a training. Data training, it is R sample training. So there is no need to mention the package. I'm doing so in order to give more information about the source of these functions. So data initial split, and then data testing, it is R sample testing data initial split. So it is important to set seed here to something in order to make the study replicable. And I'll run it, and we can have a look at data training glimpse. So you remember that we had 10,000 records in the initial data table, but now we have 80% of that in the test, in the training, and then the 80% is composed of 8,000 randomly chosen observations using stratified sampling. Okay, so this was about split and partitioning for now. The next step is preparing a recipe. Okay, data pre-processing actually. So the package of TidyModels for data pre-processing is called recipes. It is like a recipe when we want to prepare our data for the modeling. And using this recipe and developing the logic, the rationale behind developing and putting this package as part of TidyModels is the idea of considering pre-processing as an integral part of modeling, or better to say machine learning modeling. So we used to consider only the fitting part as part of the modeling, but there's a better way to look at it. At least it seems so, based on the perspectives of developers of TidyModeling and considering the pre-processing as part of the modeling. So let's define it. It is, we want to have the training data, pipe it into recipe, and the formula, and that's the minimum that we can have and we should have, and we call it recipe. Okay, or let's say data recipe. And the y object couldn't be found, so okay, I have something, data training, sorry for that, and we have now data recipe. There are many interesting functions on data recipe. If we have time, we will come back and I will show you, especially if you want to check them start with a step as the starting of the verb of the verbs, and this step is this set of functions are very convenient way to do feature engineering, okay, to improve the condition of your data set for machine learning modeling. But as we want to do the minimum for this session, we are very happy with what we have, a recipe. Okay, in the next step we would have method definition. So by the method, I also call it model. Okay, the TidyModels package for the models is parsnip. We can use parsnip, and there is an add-in in parsnip, and it is parsnip add-in. We can use parsnip add-in to search among the readily available models that we can use currently inside of the TidyModels. It means that there are other machine learning models outside of TidyModels and parsnip, but they are not ported yet into the TidyModels realm. So parsnip, and they're not yet ready to be used. So let me cancel it. If we run this, we will get a shiny way, okay, an applet. Our problem is regression, and what I want to use is a decision tree. So I wrote the decision, you can write a tree, and we have a decision tree, and it's coming from R part. So it's ported from the R part and ready for us to use here with inside TidyModels. So I click write the specification and I click done, and we have everything that we want. So we put it here, decision tree R part specification. I call it, previously we had data recipe and data training. I call it data model, or better say predictive model, to make it more explicit. And you can see that a decision tree has at least these three hyperparameters: tree depth, minimum number of observations in each leaf, and then cost complexity. You can you can code, or better to say hard code, these hyperparameters. Instead of tree depth, you can say that, okay, maximum tree depth is 10, now at least I want 10, or let's say 15, at least number of observations in each leaf, and then cost complexity is 0.01. Okay, so in this way you have defined the values of the hyperparameters. But it's very common that we want to use hyperparameter tuning to find the best hyperparameters. To do so, we need to define these hyperparameters with this placeholder of tune. We are telling the modeling that we will tune these hyperparameters later. So it's a lazy evaluation. Nothing will be actually run before its time that is absolutely necessary. So we set engine to R part. It means that use the R part package for the decision tree, and the mode is regression, because our data set, the target variable, is a numerical continuous variable. And if we run it, we can get the model, have a look at it. We can see that main arrangements, or main arguments, sorry, cost complexity, tree depth, and minimum n. Okay, workflow. Workflow is a sort of wrapping up the the pre-processing and the modeling in one bundle, let's say. Okay, so we add this one. We can say that it is from parsnip anyway, and we can check it. So this is from parsnip, this is from parsnip, this is from parsnip. We can check it, and that's true. So for the workflow, I call it data WF, and a workflow, and we add the model, or we add the recipe, which is data underlined recipe, and we add the model, which is data underline pred model, and all of them are coming from workflows package. So once again, it's not necessary to use this workflows, but I wanted to give more information about the region of these functions. And if we run it, everything seems fine. And if we click on the if we call the data WF workflow, we can see that it's a workflow. The preprocessor is recipe, the model here, and it's a decision tree, etc. So all the information here in one bundle. Okay, so what we have done till now, we defined we generated the data set, we synthesized the data set, data pre-processing, and then a model and method definition, and then wrapping everything in workflow. Now what we want to do is hyperparameter tuning. Hyperparameter extraction is the first step. We want to attune our hyperparameters. How to do so? First, we need the hyperparameters. So there is a function extract params set dials. It is from dials package. And what we need to do is we can use the workflow, doesn't matter. And if we run it, we will get an error. It is not an exported from. So it's not from dials. I'm doing a mistake. Let me check extract parameters set dials, and it is from tune. Sorry. So yeah, rationally it is from tune. We are on the hyperparameter tuning. The main, at least the main, because I'm not sure whether it's the only, but I write it in a conservative way. So the main package to be used here is tune. So we use tune to extract the hyperparameters. So hyperparameters, or data hyperparameters. Yeah, I still keep the data in order to say that what we are doing is related to that specific data, and we can recall this this object. So 3 parameters here. Now what we need to do is we need to give these hyperparameters some values. So for instance, we want to try tree depth of 10, minimum n of 15, and cost complexity of 0.01. And we want to try tree depth of 2 and minimum n of 5 and cost complexity of 0.05, etc., etc. So different combinations. How to generate these different combinations is a topic by itself. There are uniform sampling out of the hyperparameter space. There are random sampling. There are in-between approaches. Let's go for random sampling. So from tune, grid, let me check it, grid random. So grid random is from, as I said, it is from dials. So it is besides dials. So dials is something that we are using here, and we use the data hyperparameters, and we feed it to grid random, and there is a size here. Let's put it on 2, and we get 2. Let's put it on 1. We get only one combination of our hyperparameters. Let's put it on 10. We get 10 different combinations. Okay, starting from tree depth of 1 to 15 and minimum n of 13 to 36. So probably you can define the range of these hyperparameters, but for now this is fine because I wanted to show you the minimum, right? So the size 10 is totally fine. We define it as data hyperparameters grid. Okay, so now we have a grid. And then what else? In order to evaluate these combinations of hyperparameters, we need the performance evaluation approach. And the best that we have, at least from the practical side, is cross-validation. So let's go for actual hyperparameter tuning or hyperparameter tuning, yep. And we need to do cross-validation, or better say cross-validation for hyperparameter tuning. And for the class validation, we have folds or vfolds, if I remember correctly. We have vfold CV from the package or sample. And what we need to do, we need to use our data training. So let me see it as the data that we need to use, and this R sample vfold CV. It has one interesting argument. The V, the folds, 10 folds is fine to me, and then it is a strata that we set it to Y, and then it has so we have folds and we have strata. I think this is enough. We have 10 folds, and let's call them data CV cross validation. And if we run it, there is no error, thankfully. And if we call this one, we will see that we have fold 1, fold 2, fold 3, fold, etc. So in a loop over these folds, first fold 1 would be kept as the assessment, and then fold 2 to 10 would be considered as a training part. A model, the first model with these hyperparameters would be fit to the training and would be tested on this one. And the same model would be fit on fold 1 and tested on this one. And then it would be fit on these and tested on fold 3. So we have two loops here. We have two loops, and these two, one over the folds, one over the hyperparameter combinations. Okay. So after the class validation, let's go for hyperparameter tuning or searching over the grid. This can be both. And we have the function tune grid. It is coming from the package tune. And logically, it will need our data workflow. And for resamples, it needs our data CV. And then how to measure for metrics, we have a function set metrics set. So from the yardstick, we have the set, okay, metric set. And for the metric set, we want to use RMSE. Okay, without this metric, so this argument is optional. By default, the most common metrics would be used, but let's define it based on what we want. RMSE, root mean square error, or any other metric that is available in the yardstick package. So we have the workflow, we have the cross-validation samples. What we need is actually the grid as well. So tune grid, I'm not sure about the arguments. So we have the grid as well. The grid would be data grid, data hyperparameter grid. And what I'm going to do, I'm going to use system time here, starting time, and I'm going to use system time here, ending time, and I'm going to print ending time minus starting time. Okay, in order to get in order to have a measure for the performance, as we are doing everything in one single core. Okay, so we have data CV, and let's check it with an example in the help. Tune grid, okay, the model, the recipe, the folds, and the grid. So our grid is more advanced, and that's good that we have something else. Okay, the outcome would be a table. So we call it grid, we call it hyperparameter tuning outcome. Okay, and use all. Okay, this is it, and let's try it. Okay, error, invalid connection. So what does that mean? What does that mean? Let me fix this error in silence. Is it related to parallelization? Think so. But even though I have not done anything about it, so I'm not sure what to do. Let's try to run this example. Okay, so this is a problem beyond my code. Think that do parallel, there is a stop, seal, stop. So let me check. It is register stop implicit clusters. And then it is the problem of connection. Let me search the web. It says that this function might resolve the issue on register, and now yes, it has resolved the issue. So we have the resamples, we have the grid, but we do not have the metrics. Okay, you know the argument to request for a specific metric, and over 17 seconds everything is done. We can now call the function, and you can see that the output we can define. So let me put this here, metrics equal to metric set and RMSE. So later we will use this RMSE, but here how to get the results. It is a table, so we can work with it the same way that we work with any other table. We will do on nest dot, or first select metrics, and then we will do on nest dot metrics, and now we get the metric. And let's have a better look at this. So the first three columns are the arguments, are the hyperparameters, and then we have the metric. So by default, RMSE and root square error, I think, are being used. And what I want to do, I want to filter metric equal to RMSE, and I want to arrange it from the lowest to the highest, arrange dot estimate. So now we can see that cost complexity of 3.3 multiplied to 10 power minus 4, tree depth of 12, and minimum n of 27. This is the combination that reached to the best possible error, which is 1.06. So still it is a little bit there is a little bit room to reduce this error. 1 would be the ideal because we defined it in this way. Okay, and what we can do is a few things. So we saw, and then what I want is a slice actually min order by dot estimate and equal to 10. So no more arrange in order to have a tractable output. And then there are a few functions that would help us. And this hyperparameter tuning outcome, one of them is show best, which shows the best combinations of hyperparameters. The other one is hyperparameter tuning outcomes select best. And select best selects one of them. Okay, so we have cost complexity, tree depth, minimum, and then .config. So this .config would be ignored. And actually what we can do, we can also slice the minimum 1. Okay, the slice minimum n equal to 1. It would be exactly the same. So we can extract it without referring to select best and show best. And select best all are from tune package. If you do not want to learn more functions. Okay, so let's do it once again and record the time. It was around 17 seconds. Okay, so 16 seconds, 17 seconds. What we can do here, we can parallelize this process. So single core, and then we can copy this tuning to make it parallel. Multi-core performance. In order to do the multi-core performance, we need to come back to the libraries. There's one library, do parallel. We need it for parallelization. And there are a few functions that we have to consider. As far as I remember, okay, I try to remember them. Okay, I checked my notes rather than remembering them. There's no need to do so. One is cl make p sock cluster from package parallel, and then using the number of cores. So there are different ways. There are different ways to do this parallelization, and the do parallel package is chosen because it is OS independent. So no matter whether you use Windows or any other machine like Linux or Mac, it works, which is fine. So what we can do, actually, we can check the number of cores using the parallel package. I have 16, which is a respectable number, and I think 8 is very common. So here I can assign the nodes. The thing is, you should not assign all the cores of your CPU to this process because it has a limitation also on RAM. For every core, the data is copied in the memory once. So if you use 16, then the data will be copied 16 times. And for the first few cores, the processing time is reduced drastically, and then it has a diminishing rate of return, let's say. So I'm going to use 10. the number of cores to be used, 10, and then I will use this register parallel CL, and we do the system, and then here I stop it. I think these two must be considered as part of the process. So we had 17 seconds there. Let's see that what will be the time here. Okay, so we have around 7 seconds, which is a great improvement. So it's more than half, or lower than the half of the time that was used. Still, with 10 cores, we expected maybe something like 1/3, 1/4, but this around one half, yeah, it would be good. And for larger problems, for this problem, it's okay. And yeah, so we have this tree depth of 8, minimum of 23, minimum number of observations in each leaf. Okay, so we have the hyperparameter tuning, and select best data, best hyperparameters. Let's call it best hyperparameters. So we also have the performance of this model with this set of with the best hyperparameter values, with the, not the best, but let's say the optimum, from the output of the grid search or hyperparameter tuning. So no need to do it once again. What we need to do is we need to fit the model with these hyperparameters to the whole training dataset to optimize the parameters this time. There are two ways that we can do so. One is with fit function, the other one is with last fit function. So this was hyperparameter tuning. We have the hyperparameter tuning CV. Okay, hyperparameter tuning. We have the hyperparameter tuning, and the hyperparameter tuning is done. So now it is the story of updating our workflow, fitting on the training, fitting on the whole training data set, i.e. optimization of the parameters after we have optimized the hyperparameters. So what we need to do is updating the workflow with the optimum hyperparameters. And how to do so? We have data workflow, and then we have a function finalize workflow, and parameters, we use the data best hyperparameters. If we run it now, this time we can see that the main arguments, they have values. Call it find our workflow. Okay, and then one, two, three. So a last fit. As I said, there are two functions to do so. So set seed 8 or 9, doesn't matter. We can use this final workflow and fit it to data training. This is the data training, and if we fit it, we call it last data last fit. Okay, and this is the data last fit. We have a very large actually tree, and we can, using fit, there are two functions to fulfill this step. One is fit and the other one is last fit. They are supposed to yield identical results, yet there might be discrepancies due to the internal random seeds, and even the with parallelization we have the same issue. So we have this last fit. What we can do is data last fit, we can extract fit engine, let's say fit engine. Okay, this is the extract fit engine, and because it's a decision tree, we can use another function which is rpart plot, and another function library VIP. This is for plotting decision trees of rpart. This is for VIP variable importance visualization. Okay, so the variable importance is not that much of a thing because we have only two variables. It's very easy to say which one is more important. But from the rpart plot, there is a package, there's a function of rpart plot. If we use it, we get this huge and deep tree. Okay, not even readable properly. And if this is for exploration, this modeling, then we have to restrict the size of the tree, otherwise it is not very useful. Okay, but for now it is okay. We can extract the fit engine and get such plot. And even I guess that, let me try to extract. So we have parameter dial, recipe, workflow. Let me check my notes. Okay, it's extract, fit, parsnip, and then VIP. That X1 is more important, but let's not have anything here except this one. Even this one is not necessary. So the last step would be, we have fitted. Okay, what about the last fit? The last fit would be in this way, that we have final workflow and last fit, and this time instead of feeding the data training, the data initial split, the split would be used. Okay, the same problem. That's very interesting. The same problem. Let me resolve it with the same function. So now we can get it. So here we call it data last fit, and this time we have this last fit. Okay, it doesn't matter, both of them should get the same results. I like the fit because this is a more practical, so you don't need to learn a new function beside fit. You can use fit on other occasions as well. So this is it. Now, prediction on new data. Generating the predictions. And we have this last fit, which is a better thing to me. Data last fit. Okay, we use predict, and then new data is data testing. Now let's see what we get. We get a dot pred, and we can bind calls with testing data. So data testing, and we have dot pred here in x1, x2, and the y. And then from the yardstick package, you can get different metrics, RMSE, and the truth is y, and the estimate is dot pred. So we can see that the RMSE is calculated. Without that, it is also very easy to calculate it. Let's do it. So you need to mutate. We define error as dot pred minus y. And then we need to power this by 2, and then summarize cross error with min, or square RT and then min. Okay, the summarize is problematic. So let's put an X here, and what else now? Okay, so it is the exact same value. You can calculate it. What I'm showing you is you don't need all these functions to remember all of them. You can calculate them easily using the tidy dialect of dplyr and other packages. There are other functions that we can use. As one of them is tidy for the model, the other is glance, etc., etc. But this is the minimum. We have the predictions, and we have the performance on the predictive model, so on the new data set. And this is the end of the session. So let me check the time. In around 1 hour, a little bit more, because I had a strange problem with parallelization. But we reviewed how to work with TidyModels at the bare minimum yet practical level. And see you in the next video.